when I took first year calculus, I found the ideas and the concepts amazing. What I didn't find so amazing were the homeworks, because they were all the same thing. Here's 2 dozen integrals, evaluate them with the technique of the week. They were just drills. They took all of the creativity out of mathematics. And in my opinion, the creativity is what makes mathematics so fascinating. Thankfully, towards the end of the semester, my professor introduced us to the Gaussian function. This is the classic bell curve that you see in probability. It looks something like this. We'll use x and z. And the question is, what is the area under this curve? So in particular, evaluate this integral over all space. Now, as first-year calculus students, the instinct is to try use substitution. But that gives an integral that's got fractions and exponents and radicals, and it certainly doesn't look any easier to solve. Try integration by parts, but similarly, you don't really simplify anything. You're still left with this e to the negative x squared term. So what do? Well, the observation to make is this symmetry across the z-axis. This symmetry allows us to effectively spin the Gaussian around the z-axis. So I can sketch a contour plot here, right? If we imagine the z-axis coming out of the board, this is x, this is a new variable y created because we spun. I could imagine taking a point on the Gaussian and spinning it around, creating a sort of mound. And this is a circle. Now, perhaps this is just my hubris talking, but I like to think I understand circles fairly well, certainly better than I understand the Gaussian. And if somebody were to ask, what is the volume under this surface of revolution that I've created, I would say, well, that's not so bad. I can think of it as integrating a bunch of cylinders. So the height of the cylinder is going to be the Gaussian, and then I can take the circumference of the circle, dr, and there you go. And this isn't so hard to evaluate, because I have this r here. So you can imagine use substitution. You've got r squared up here, 2r down here, that could work. You could even just use the fundamental theorem of calculus and treat this as an antiderivative. It's not hard to evaluate. So we have a way to graphically go from something we don't understand to something we do understand. Now, do we have a way to bring the integral, to convert it to a form that we understand? And we do, but we got to get a little creative. And here's the magic. We're going to take this thing we don't understand, and our approach to solving it is going to be to make it more complicated. A very mathematical approach to things. So we're going to square it. And the note to make is that we can separate this into its factors, the two integrals, and it doesn't matter what symbols I use. They're just symbols. Once I evaluate the integral, they're meaningless. I could use x, I could use y, heck, if I had time, I could sketch Van Gogh's Starry Night. I'm going to use y in this case because I don't have the time, but feel free to use your imagination. And because this is in terms of x, and this is only in terms of y, we can combine the integrals to get something that looks like this. And now we sort of get a sense of where we might get our circles from. Because x squared plus y squared is, if we convert to polar, just becomes r squared. So let's go ahead and do that. Let's convert to polar. Integrals. So our Gaussian, as I said before, becomes e to the negative r squared. dx dy, in converting to dr d theta, we have to apply our Jacobian. So that gives an extra term r. And already I'm getting excited because I'm seeing something I could use substitution on. But before that, let's not get out of ourselves. We've got to fix our bounds so that we're still covering all of the xy plane. So 0 to pi. And just as before we combined our integrals, here we can separate because theta does not play a role in here. So we can effectively move d theta out of the integral. But then the integral of 1 with respect to theta from 0 to 2 pi is just 2 pi. And so we're left with 2 pi integral from 0 to infinity e to the negative r squared times r dr, which is exactly what we had when we went by the graphic route. And like I said, this is fairly easy to solve. And if you do so, you'll get pi. That's right, this thing that we couldn't solve, that seemed so complicated, just evaluates to pi. But there you go. There's an answer. Now we have to keep in mind, right, that we squared what we were interested in. So this is really the square of our answer. What we really want is the square root of pi. Just to bring it all full circle, our final result, this. And I find this beautiful, not just because of the many applications of the Gaussian function, but because of how it exemplifies the way that creativity, the way that thinking outside the box, or outside the circle in this case, can really expand one's capabilities in calculus.